Now Marcel Hunting will start his presentation on analyzing infeasible problems in AIMMS.
Okay, thank you, Chris. Yeah, one of the more challenging tasks in mathematical programming is to find the cause of an infeasible math program. So infeasibilities may occur as modeling errors when you are developing a new model, or due to inconsistency in the model data. So to find infeasibilities, you have to act like a detective. So you have to look for clues, use deduction and logical reasoning to find the constraints or variables that make the problem infeasible. And AIMMS offers tools to help you with that, so for analyzing infeasible problems. And these tools can be seen, or they act as magnifying glasses, as a magnifying glass. So these are not miracle tools, so these tools will only help you to detect infeasibility, but it's not like if you switch on or if you use that tool, then it will automatically find the infeasible constraints or variables for you. That is quite rare that it will happen. It might happen, but often you also have to do something yourself. So this is an overview of this presentation. I will start with saying something about unusual solver termination. That is usually not the cause of an infeasible problem, but it's related, so I want to make a note, tell you something about it. And after that I will present four tools that can help you detecting infeasibilities in your model. So the irreducible infeasible set is the first one. Then another approach is using access variables. A third approach is using the AIMMS Presolver, and the last approach is the Farkas infeasibility proof, which is a recent added feature of the solvers Cplex and Gurobi. So let's start with the unusual solver termination. So here on the left you see a possible program window, and here we see the program status is intermediate infeasible. And the solver status is a resource interrupt, and we can also have different solver statuses like terminated by solver, setup failure, or solver failure, so the ones shown in the red box. And they often correspond then to one of the program status in the green box, so intermediate infeasible, intermediate non-optimal, integer solution, or no solution. And if you have one of those combinations, that usually means that something strange or unusual was going on in the solver. And what's the best way to deal with that? Well, that's two things. You first could check the message window, which you can simply open by pressing Ctrl and M at the same time. And if that doesn't give any clue, I really recommend to start logging solver output. That means you have to make sure that the solver creates a solver log file. And that is done by setting the general solvers option solver listing message, which is shown here. You should set it to all. And then depending on the solver, you should set another option. For instance, if you want to use Cplex for solving an MIP, you should switch on MIP display to one of the value, for instance, display each end node. If you are using Gurobi, you should switch on the option output file. And if you're using Carnapt or Nitro to solve a nonlinear problem, you should switch on the option status file display. And once you have set these options, the solver or AIMMS will print a solver log file in the log folder of your AIMMS project. And that file often contains a lot of very useful information and might give you a clue what's going on over here. So that's all I want to say about this. So now for the rest of the talk we will focus on really infeasible problems and how to deal with them. So the first approach that you could use is using the irreducible infeasible set. It's sometimes also called differently, like irreducible inconsistent system. And the definition is, it's an infeasible subset of constraints and variable bounds. So it's a subset of your constraints and variables in the model, but only such that it's if you take that subset, the problem is already infeasible. And the idea is to make that set as small as possible so that you can investigate it easier. So the formal definition is that if you this subset becomes feasible if any single constraint or variable bound in this subset is removed. But for now, I just want you to remember that it's only a small subset. So forget the second part of the definitions. Most important part is that it is an infeasible subset of constraints and variable bounds that is calculated by some kind of algorithm that is implemented either in the solver, so you can use the solver functionality directly, so from Cplex, Gurobi, or XA, or another possibility is using the MetProgram inspector, and there it is called irreducible inconsistent system. And so the MetProgram inspector uses an algorithm that's implemented in AIMMS. And the IIS, so for short, is only available for LP and MIP, so only for linear problems and for quadratic problems. So I'm going to demonstrate this by using an example. This is a farm planning example, which is also an example available in the AIMMS library of examples, only I changed something, I made a mistake somewhere. So if I solve the problem by running main execution, that contains a solve statement. If I do that, and you will see that Cplex returns program state is infeasible. If I choose a different solver, say, let's say Gurobi, then Gurobi returns the state is infeasible or unbounded, but we already know it's infeasible. So to use the IIS from the solver directly, what we have to do is we have to switch on one option, namely the option that can be found in solver's general, standard reports, solution, and then Infeasibility Finder. We have to switch that one on. And then we can run again. We have to solve again. And now the IIS, so the system, the set of constraints and variables that makes the problem infeasible, is written to the listing file. So we open that one over here, open listing file, and here we can see that Gurobi constructed the following IIS, and this time it consists of 3 constraints and 4 variables, or the variables are displayed over here. And the logic that the solver is using is not always directly trivial. I mean, if we are effective that all the variables that are shown here are non-negative, so amount planted, sales, and fraction consumed are all non-negative. If we use that information, then for the first constraint we can already see that both amount planted variables should be 0. Then from the second constraint it follows that this one is 0, that all other variables in this constraint should be 0, so all the 3 fraction consumed variables should be 0, and that leads to a contradiction with the last constraint, because the left hand side is 0 and the right hand side should be 1. But that's not the logic the solver is using. In this case, the solver doesn't use the information that amount planted maize is non-negative, because it's not over here, and also doesn't use the information that fraction consumed first is non-negative. So the logic the solver is using is a little bit more complex in this case. But the IIS, if you look at this constraint and know that all variables are non-negative, then you can indeed see that it is correct. And the IIS is not unique, so there might be different IIS possible. If you would use it, for instance, if you would solve the Cplex, it could give you a different IIS. Another way to calculate the IIS is by using the MetProgram inspector. So then we open the MetProgram inspector by going to Tools, Diagnostic Tools, MetProgram inspector. And here we can see the MetProgram solution that indeed the problem is, well, infeasible or unbounded. In this case we know it's infeasible. What we can do now is to click Actions, Irreducible Inconsistent System, IIS. And if we do that, then AIMMS will use an algorithm which underneath calls Gurobi, but it will use its own algorithm, and then it finds these variables in the IIS. So we have 4 variables again, and we have 3 constraints. So in this case it's the same IIS as shown before by Gurobi directly, using the Infeasibility Finder. And here we can click on the variables to get some more information. And we've seen before that if amount planted is 0, then we get some kind of we get an infeasibility, so something probably is wrong in this constraint, and indeed that's the case. If you look at the data over here, and you see it's 5 everywhere except for June there it's 0, so that's apparently a mistake in the model. So in AIMMS there are two. In AIMMS there are two approaches to use the IIS. So we have the Infeasibility Finder, which uses an algorithm in the solver, so in Cplex, Gurobi, or XA. And we have the MET program inspector, which uses an algorithm in AIMMS, but underneath it calls in a solver, but the algorithm itself is implemented in AIMMS. Not every solver has the possibility of calculating an IIS. For instance, CBC cannot do it. But on the other hand, if you only have CBC available as linear solver, you can use the MET program inspector that can also be used for CBC. The Infeasibility Finder is also available for quadratic problems, at least if you use Cplex or Gurobi, so for QP, QCP, and so on. The MET program inspector is only available for linear problems, so only LP and MIP. And for MIP problems, Cplex and Gurobi have a special algorithm that makes use of the integrality of the variables. The MET program inspector doesn't do that. If that has to calculate the IIS for an MIP, what it will do is it will relax the MIP and then calculate the IIS for the relaxed MIP. Often, if an MIP is infeasible, then also the relaxed MIP is infeasible, so this approach is not that bad. But sometimes, in some cases, the infeasibility comes from the integrality. Note that to calculate the IIS, the algorithm has to solve multiple times in MIP if your original problem was an MIP. So if your original problem is a large MIP and a difficult MIP, then also calculating the IIS for that MIP might be very, very hard to do. So it might take some time sometimes. And I said before, the IIS can only be used for linear problems and quadratic problems, so it cannot be used for NLP, mixed integer nonlinear programming, or for constraint programming. The second approach, or the second tool that AIMMS offers for analyzing infeasible problems is by adding access variables to the problem. So up here I have a linear problem where the constraints are separated in 3 sets. Namely, we have the first set with greater than inequalities, the second set with less than inequalities, and the third set is with linear inequalities and might be minimizing or maximizing. And then you can create what we call a feasibility problem by adding access variables. In this case, we have a variable u that denotes a positive violation and a variable v that denotes a negative violation. The positive violation is added to the greater than inequalities and to the equality constraints. The negative violation is added to the less than constraints and the equality constraints, and both u and v are non-negative. So the idea is to minimize the sum of the infeasibilities, and in this case we have a weights of 1 for u and v, but the weights could also be different as long as they are positive. And the nice thing about this feasibility problem is that it's always feasible and it's also bounded. And of course, if you solve the feasibility problem and it appears that u and v are 0, both are 0, then it means that the original problem would have been feasible. So in AIMMS there are three methods are using the access variables, namely the MET program inspector if you choose the action substructure causing infeasibility. You can also use violation penalties. In that case you have to define a parameter with an index domain, index variables constraints, because that parameter will then mark which variables and which constraints will be part of the calculation, to which variables and constraints access variables will be added. So that parameter should be defined, but I will demonstrate that in a couple of minutes. And the third method is by using the GMP functionality. So in this case, it's a function GMP instant create feasibility. I will not demonstrate this function. I only will say also that besides minimizing the sum of infeasibility, it can also be used to minimize the maximum feasibility, which is a different measurement. Okay, now I will demonstrate how you can use access variables by using the Program Inspector. Sorry, wrong problem. Okay. Okay. So if we solve the problem once again, it's infeasible or unbounded by Gurobi. We open the Program Inspector again. Here we have now an action causing substructure, causing infeasibility. We click that one. And then in this case it only shows one constraint, namely the constraint which restricts the amount planted to 0. Because we've already seen before that all the data is 5 except for June where it's 0. So in this case, for this example, using the Program Inspector and then using substructure causing infeasibility immediately gives you the single constraint that causes all problems. This is a nice example. So if you have a bigger problem, then it might not be as nice as this, and then you have to do more investigations yourself. I will use another example to show to demonstrate the violation penalties, and that is this pooling problem, which is a nonlinear problem. So the idea with access variables can also be used for nonlinear problems. That's a nice bonus. So it's not only restricted to linear problems. And if we solve this nonlinear problem, in this case, then Conrad will conclude that the problem is locally infeasible. So to use the violation penalties feature in AIMMS, we have to introduce a new parameter. So let's call it a VP, and then we have to use an index domain, index variables, constraints. So with this parameter we can mark which variable bounds and constraints should be inside the should be part of calculating the penalties. We could also restrict only to the constraints. In that case, we can only use we could use the index constraints index, which is a subset of the other set we shown before. And now we have to assign the data. What's shown here is also including variables with the definitions. For instance, the first three have a definition, are variables with a definition, so pool amount, and the third one is the objective. We don't want to include them now. We could include them, but now we don't do that. We only want to have to use the real constraints, and we could use a penalty value of 1 or whatever. We could also use 3 or something. And we close it. So now we have the data. We have selected these constraints. The next thing we have to do is use this parameter that we just created before. It should become the violation penalty in the MET program. So we type it here. And then another thing that we have to do is to disable the old objective, because by default, if we use the violation penalties, the original objective will be included, but that could lead to an unbounded problem. So we likely want to remove it. So that's what we do now. Now we can solve the MET program again. We see that we now kind of solve the feasibility problem, which is a feasible problem. And we could investigate the violations now by using the violation suffix of the constraint. But that's a quite cumbersome way to do it, because then we have to write down display constraint.violation. An easier way to do so is by using the MET program inspector. So that's what we're going to do again. Open the MET program inspector. Here above we see that AIMMS added some new variables. So variables with positive violation, negative violation. Apparently flow balance is an equality constraint because it has a negative violation and a positive violation. And now we can look at the variable solution. We are only interested in the variables that are named positive violation or negative violation, and we are looking for a variable with a non-zero value, and over here we have it. So over here we have one. So we have for final product amount required lower bound, which is a constraint. The negative violation gives a non-zero value. So we might inspect that constraint. We should inspect that one. It's over here. It's gives a lower bound for some of the variables. We can inspect the data. So we see here the data. Then also we have an upper bound for this constraint. So we have an upper bound for the same sum. It's not a part of the. It was not part of the corresponding violation variables had a zero value, but we might nevertheless still inspect it. So here we have the upper bound. If we show the data here over here, then we see it's 17, and that's so the minimal value is higher than the maximum value. So that's inconsistency. So we found the infeasibility. The third approach that you could use, or the third tool in AIMMS that you could use for analyzing infeasibility problems is the AIMMS Presolver, and that is especially useful for nonlinear problems. So the AIMMS Presolver does a lot of pre-processing, and one of the things it does is bounds tightening, which I will demonstrate by using this example, this small example. So we have a variable x with a range 10 to 100. We have a variable y with a range 5,8 and a variable z with a range 1,8. And assume we have this constraint, so x plus 4y minus 2z is equal to 60. Now by using the bounds of y and z, we can deduce new bounds for x, and it goes as follows. Of course, because this equality holds, we know that x should be equal to 60 minus 4 times y plus 2 times z, which is smaller than or equal to 60 minus 20, so 20 is 4 times the lower bound of y, it's 5, so 4 times 5 is 20, plus 2 times the upper bound of z is 2 times 8 is 16, which gives you as a new upper bound for x, it's 56, and in the same way we can construct a lower bound. In this case for y we use the upper bound, so because y has a minus coefficient, so 4 times 8 is 32, and for z we use the lower bound, so 2 times 1, and then we have a new lower bound for x. So any solution that satisfies these constraints and these bounds, for any solution that satisfies that, the x should be in the range 30 to 56. So if we would have had another constraint in the math program saying, for instance, x small or equal 20, then we have an inconsistency, and the AIMMS Presolver will determine that, will detect that and return that. So that's how you can. So that's how the AIMMS Presolver detects infeasibilities. And it also can do it, this is a linear constraint, but it can also do the same kind of analysis with nonlinear constraints. So I'm going to demonstrate this by using another example. This is a delayed constraint routing problem, which is a mixed integer nonlinear problem. So if we try to solve it, it will use Baron in this case, and Baron will show that it's infeasible. Baron will note that it's infeasible, but unluckily Baron cannot tell us, at least this version of Baron cannot tell us why the problem is infeasible, so it can only tell us that it's infeasible. And in case of Baron, because it's a global solver, we for sure know that the problem is infeasible. So now we want to use the AIMMS Presolver. We activate it by setting some option, namely solve a general AIMMS Presolver, and then we switch on the nonlinear presolve. You can also the AIMMS Presolver can also be used for linear solvers, but linear problems, but usually that's not very useful, because linear solvers have their own presolve, which is much more advanced than the AIMMS Presolver, which is more dedicated to nonlinear problems. And we also want to display the infeasibility analysis. So we also switch on this option. Apply. Now we have to solve the problem again. by running main execution. And now we see that the AIMMS Presolver concluded that this problem is infeasible. We can again open the listing file, and this shows the pre-solved infeasibility analysis for this MET program. So apparently this MET program contains the constraint demand satisfaction 91, which says that demand fraction 91, 1 should be greater or equal to 1. So this constraint already fixes this variable to 1. So the lower bound can be improved from 0 to 1. There's also a second constraint, namely flow definition, which says that the flow of 317 should be greater or equal to all the sum of the demand fraction shown here, including the demand 91.1 over here, of which we know it should be 1. So then we can deduce that flow 317 should be greater or equal to 2.7 times 1. So that's what we see over here. So the AIMMS Presolver can tighten the bound from flow from 0 to 2.7, but apparently there's another constraint, namely capacity constraint 317, which says that flow should be smaller or equal to 2, and there we have an inconsistency because it should also be at least 2.7. Yeah, so we might, now that we have seen this analysis, we might inspect the constraints that are mentioned here. So let's first look at demand satisfaction. This is a constraint which looks okay. It's a definition. It's a summation which is bounded by 1. That looks okay. We also have flow definition, and that uses some parameter over here. So the constraint itself looks okay, but the data here might be incorrect. So let's check it. So we have a parameter over here, and here at first sight nothing strange is there. So we only have one constraint left, which is a capacity constraint, which limits the flow. And then we might check this data, so the arc capacity, and we see here a lot of big numbers, and we had the constraint for 317, so we have to scroll down, and here at the bottom we see that they have a lot of small values. So probably here something is wrong with the data. So this shows how you can use the AIMMS Presolver. So for nonlinear problems, AIMMS offers less amount of tools. For instance, the IIS cannot be used for linear problems, at least not directly. So for nonlinear problems, you have to notice that AIMMS offers a lot of local nonlinear solvers like ConOpt, Nitro, SNOpt, IPOpt, or AOA, and they are local, meaning that they only will only find the local optimal. So they cannot guarantee to find a global optimal solution, and it might also sometimes happen that they are stuck in a local infeasible solution while in fact the problem is feasible. So they might return infeasible while in fact the problem is feasible. So there are two approaches which you can use for analyzing infeasibility with nonlinear problems, namely the AIMMS Presolver as shown before, and also the violation penalties, which can also be used for nonlinear problems. But I have to warn you, for an infeasible problem, the AIMMS Presolver often cannot find an infeasibility because it only does do bound reduction techniques, and the infeasibility might be somewhere else. So there are quite many cases where the AIMMS Presolver cannot detect the infeasibility. And what you could do in that case is that you use another approach. For instance, you could temporarily remove all the nonlinear constraints from your problem. Then you get a linear problem, so it might be an LP or MIP. And you can then check whether the resulting linear problem is infeasible. If that's the case, then you can, for instance, use the IIS again. The last approach I want to discuss is a new approach, or fairly new. It's a fairly new feature of the solver CPEX and Gurobi, and it's called the Vargas infeasibility proof. I will demonstrate it by a small example. Assume we have three variables, U, V, and W, which are all non-negative, and assume we have this system of 3 inequalities, then at least to me it's not quite trivial to see why this system is would be feasible or not. What we know is that if there's a solution to this system of inequalities, then that solution should also be feasible if you, for instance, construct a new constraint which sums up all these variables. So if you use the summation of these three constraints, sorry, I meant constraints. If you use the summation of these 3 constraints, then any solution to this one should also be feasible to that new constraint. And that even holds if we use positive weights for these constraints. So for instance, we could use the following weights: the weight 0 for the first one, the weight 2/3 for the second one, and 1/3 for the third one. If we then sum up these constraints, we get the following constraints: minus v minus w greater or equal to 8/3. So any feasible solution, if this system is feasible, then any feasible solution to this system should also be feasible to that one. But clearly, because v and w are non-negative, this cannot hold because the left-hand side is at most 0. So this implies that also the original system was infeasible. So what we have used now is in fact more or less we have used the famous Farkas lemma. And the coefficients, the red coefficients over here, which I will call the Farkas coefficients for ease of use, these are the coefficients that a solver like Cplex or Gurobi can calculate. They can return to you. They can return them to you, and then the coefficients that are non-zero, they are the one that involves in this, that they are part of the system of constraints that cause an infeasibility. So in this case, the first one is not part of it because it has a coefficient 0. Unfortunately, this is only available for LP problems and for Lex-MIP problems, so not for MIP and not for nonlinear problems. And what happens if we multiply the third constraint by -1? So then we get a less than equal constraint. Then we have a negative coefficient over here, so a non-positive coefficient. So for greater than constraints, we get a positive Farkas coefficient. For less than constraints, we get a negative coefficient. And for equality constraints, we can have a positive or negative. So there's no limitation there. So I will also demonstrate this one by the last example, which is a transport example. So if we solve this one with Cplex, then Cplex concludes that this model is, surprise, surprise, infeasible. What we have to do now is to set 2 options. So we have to set a solver-specific option, namely the option Farkas infeasibility proof. We have to switch that on. The same option is also available for Gurobi. And the Farkas coefficients will be stored in the constraint level value, so we have to make sure that they are stored also. So we have to also switch on the option always store constraint levels. I'm a little bit lazy, so it's over here. We also have to switch this one on, and then we have to solve the problem again by running this procedure. Oh, I forgot to do something. I forgot to display them, so I have to do it again. So I'm displaying the constraint level values of the level values of the constraints, the only constraints inside the model, namely meet demand and meet supply. And I also display the transport model, which is the MET program, using the suffix sum of infeasibilities, which gives a measurement of the infeasibility, which is also returned or calculated by the solver. So we have to solve it again, run this procedure again, and then open the listing file. You will see that for some of the constraints we have non-negative Farkas coefficients, and apparently the sum of infeasibilities, or the amount of infeasibility, was 700 in this case. And we can also see that as follows. So the constraints that had a non-negative or a non-zero value are these constraints. Here we see the Vargas coefficients, and if we use these coefficients and sum up these constraints, we get this inequality. And because transport has all transport variables have this range, so 0 to 2000, we know that this left-hand side of this constraint can be at most 2,000, so it's an infeasibility. And also the measurement of the infeasibility is 2,700 minus 2,000, it's 700, which is also calculated here. So this is how you can use the Vargas infeasibility proof. I noticed that using the Vargas infeasibility proof is not extremely user-friendly currently in AIMMS, because you have to define, you have to use the row values, and you have to spec the, you have to inspect the constraint level values. This is not always very easy to do. So we would like you to ask whether you would be interested to have a better method to use the Vargas infeasibility proof. So I have a small poll here. So the question is, how would you like to use the Vargas infeasibility proof? And the possible answers are by using the listing file, so as we've seen before with the Infeasibility Finder, something like that, or by using the Met Program Inspector. Can also be that you will never, that you think you will not use the Vargas infeasibility proof because, for instance, you have no linear problems, or you think that the other tools are better, or you have no opinion. So please give an answer, and know that the webinar polls are anonymous, so we cannot see what you have voted. We can only see the total number of votes.
Seems most people have voted. I will close the poll.
What did they vote?
25% voted they would like to use it via the listing file. 20% voted they would like to use it via the Math Program Inspector, and the rest have voted no opinion.
Okay, I have only one more slide, namely I only want to give you some references to all the information that was presented here, so references to in the AIMMS documentation. So in the language reference you can find something more about more information about the violation penalties, namely chapter 15.4, and you can also find more information now about the AIMMS Presolver in chapter 17.1. So that's a language reference for AIMMS 3.14. For all the versions the chapter numbers might be different. In the AIMMS help you can find more information about the Met Program Inspector, also about the Infeasibility Finder, and also about the Vargas infeasibility proof. The function reference gives you some information about the GMP instance create feasibility function, which can also be used with access variables. And finally, last year there was a blog post on the AIMMS blog about dealing with models that are infeasible or unbounded. So like we've seen in the beginning that we said that the problem was infeasible or unbounded. And that blog post contains also some of the information presented here. So that's the end of the presentation.
Marcel, thank you very much for your very interesting presentation. Please, attendees, please continue to ask your questions. The first question is, my model is reported to have 2 duplicate columns. What should I do about that? Marcel, please go ahead.
Well, duplicate columns are not really a sign of infeasibility, so it might they are never a cause of infeasibility, so it's somewhat off topic, but anyway. So the tools that are presented here cannot help you with that, so you have to do another way. And one thing you can do is inspect the model that is generated by AIMMS, for which you can use the constraint listing file, or you can also check the Met Program Inspector and then check these columns that are apparently duplicated, because apparently somewhere in your Met program you have 2 columns or 2 variables that are present in the same constraints with the same coefficient.
A last question that appears here. Scaling may give you unreliable results. Does AIMMS offer the features like the feasibility analysis to improve the scaling of your model?
Yes, AIMMS, but not always automatically, but AIMMS of course can use scaling itself, so you can use units of measurements. So you can specify units for variables or constraints or even for parameters, which can help you to improve the scaling of your model. And also the solves themselves, like Cplex or even CANOPT, they do also some automatically scaling, but it's done after generation of the MET program. And it's often this, they cannot fix everything. So if the scaling is very poor, they can fix some small part of that, but not everything. So if your MET program, or if your model generates a MET program that has a lot of large coefficients or very small coefficients, you might consider using units, because then the problem will be marked as poorly scaled, and by using units you can improve the scaling.
Thank you, Marcel, for your answer. Now I have a question which I can answer myself. Will this video be shared? Yes, this video, like any webinar in this series, will be shared and published once we've already did. The next question is about pre-solving. Sometimes this may take considerable time. Can this time be improved?
Can this pre-solve time be improved? I presume that the question asker is talking about, for instance, Cplex, or maybe it's also about, I don't know, maybe it's also the AIMMS Presolver, I don't know. I don't think there's much, if it's the AIMMS Presolver, there are some options that can be used to switch off preprocessing, for instance, that the preprocessor uses, for instance, nonlinear constraints. It might be that you say that the preprocessor only should use linear constraint, which could help improve the performance, but then as a downside, it might the reductions the presolver can do might be less. For Cplex and Groby or for any other solver, there's not much you can do about that. So the only thing you can do is switch off the presolver or switch it on, and there's no other. You cannot do anything else. There's no other fine-tuning.
Okay, thank you very much for your elaborate answer. Now, you have offered various tools for infeasibility. When would you prefer the Farkas method over the other methods to use first?
The Farkas infeasibility proof can, of course, only be used for linear programs. And I think that the people that use Farkas infeasibility proof, they claim that it's the most natural way to detect infeasibility. So it's not the other two ones, the IAS and the excess variables, are more artificial. The Farkas infeasibility proof is, if it's maybe more natural. To be honest, I have never used it in practice. I only used it for testing the functionality, so I don't have a good answer for when should it be used first. I only see it as a one possibility. So if the other two, so the IAS or the using access variables do not work, I would use Farkas infeasibility proof.
Okay, thank you for this answer. I'm running out of questions here, I see. Please, this is your opportunity to ask further interesting questions. They are really interesting. I do not see any other further questions incoming, so I'm going to conclude this webinar now. Marcel, can you give me control over your screen, please? No.
Of ik kan afronden met deze print.
Yes, Before finalizing this webinar, I'd like to point out the next webinar, which will also be published. Please go to this link to register at that webinar, because well, AIMMS 4 is upcoming, and it allows the use of source control. It will be presented by Koos Hering, one of our senior AIMMS developers. Now I would like to thank you for your attention and we'll conclude this webinar.